Okay, welcome back, everybody. If you recall from last time, we were exploring sequences, and we made a definition, a rather curious definition, which was that a Cauchy sequence is a sequence where all the points of the sequence get close to each other. Okay, and we wanted to try to understand what are the consequences of being a Cauchy sequence. Now, we saw that if a sequence converges, then in fact it's Cauchy. That is, if a sequence is actually converging towards a point x, then all the terms are actually getting close to each other. Why was that? Well, that was because if you want to show 2 points in the sequence are close, you can measure their distance to x, the limit of that sequence. And since those pairs of distances must be small, their sum must be small in the triangle inequality. That's the basic idea, right? And we have the question, of course, then is, so Cauchy sequences, convergent sequences are Cauchy sequences convergent all in every metric space? And the answer was no. Okay. But we make the definition that a metric space is complete if, in fact, Cauchy sequences converge. So complete spaces, being Cauchy and being convergent are the same thing. Okay? That's why complete spaces are of interest, and we want to understand what spaces are complete. So that's the major topic of today, and if there's time, we will discuss some other topics as well. Okay. Okay, great. So what metric spaces are complete? Many of you last time, I think, had a conjecture that, in fact, that R was complete. So on the way to seeing whether that conjecture is true, let's see if we can't establish a first basic fact about complete spaces. So here's a conjecture that I think some of you guessed at last time as a class of complete spaces. Compact spaces. So here's a theorem. Compact metric spaces are in fact complete. Interesting. Okay. So give me an example of a compact metric space. The interval 0, 1. Okay. R is not a compact metric space, right? Because it's not compact. It's unbounded. Good. What's another example of a compact metric space? How about finite? A set that's finite is certainly a compact metric space. Okay. Of course, convergence. Let's just convince ourselves that they're complete. Is it true in a finite metric space, one with only 5 points in it, you have a sequence? That is it true that if it's Cauchy, it converges? I have 5 possibilities, and I have to pick an infinite string of things, and they all get close to each other eventually. Then what must be true? Eventually, this sequence, which might hop around initially, must do what? Must stay on 1 and stay there because the points are getting close to each other, right? As soon as epsilon gets smaller than the minimum distance between 2 points, then all the points have to be at the same point of the space, right? Okay, so that's kind of a trivial theorem when the space is finite. Compact is a little more interesting, but not too far off that idea. So let's do a proof for compactness. I'm actually going to do a different proof than the proof that's in your book, and so you might compare the proofs. But this one's going to use the insight that we saw last time, that compactness implies sequential compactness. And so we're going to use that fact. So what we want to do to show a space is complete is to take a sequence, an arbitrary sequence, xi. Let's let that be a Cauchy sequence. Actually, let me write xn, since we've been using that as our index. Let xn be Cauchy. What is our goal? Good. Our goal is to show xn converges. Okay? That's our goal. And to do that, of course, we need to figure out what point it converges to. That would be nice to specify here. So this is in the space X. Okay. Now, since X is compact, it is sequentially compact, meaning every sequence has a convergent subsequence. Okay, how do you think I'm going to use that fact to show that the big sequence converges? The limit that the subsequence converges to. Good, excellent. So this is the nice thing about this criterion is it gives us something to latch onto. We know because it's compact, it's sequentially compact. So there exists a subsequence. Let's call it, how do we usually notate a subsequence? X sub n, and you're picking out some sequence of the n's, and that's so x sub n sub k, for instance. I'll let that second subscript be k. There exists a subsequence converging to a point of x, and we might as well call it little x in big X. Happy with that? So Jacob's thinking, yeah, I'm happy with that. That's a good candidate for the limit of the entire sequence. So let's draw ourselves a picture. Okay, so this sequence is, is doing some funny things, but we've identified a subsequence which appears to be converging to something. Maybe this point. Let me draw a limiting point, which I'll call x. And these circled points are the subsequence that converges to x. Help. I want to show now that the entire sequence converges to that point x. First of all, does everybody agree that that's the thing to do, is to show that that limit x of the subsequence is the limit of the whole sequence? Yeah, okay. Show me how you're going to do that. How are you going to show that all these other points eventually also get close to x? If I know that this sequence gets close to x, how am I going to show that? Yes, Keith.
So after some n k,
Uh-huh.
n k gets there, so you can relate n k to just n.
Okay. So, sorry, what's n?
N is from the first.
Oh, you mean take an arbitrary point, consider one point that's not circled, and past some point, this is close to what? Yeah, so past some point in the sequence, non-circled points are all close to circled points, yes? Good. And circled points are close to x. So what you're going to try to do is show then that non-circled points are also close to x, right? So here we go. We're just thinking through this proof before we write it down. We want, for any epsilon, to show that all the points are eventually within epsilon. So let me suggest doing that with a little ball here, a radius epsilon. Yeah, that's little. We zoomed in. Okay. Okay, now, help. So past what point in the sequence would you like to take a look? Well, past a point that will get you to the circled points within how far of x? How about epsilon over 2? That's a good thing to try. Good. So maybe past some epsilon over 2, they're all within, the circle points are all within epsilon over 2 of x, past some point. There's a big N for which that's true. And now, what about how far would you like to look for the Cauchy part? When they're less than epsilon over 2, and that might happen for a different index. Good. Then take the maximum of both indices beyond which both of these things are true. That's the basic idea. So, very nice argument. We're going to fix epsilon bigger than 0. We're going to start with that. And now, the Cauchy part, so xn Cauchy implies what? Well, there exists a, let's say, big N, such that if I and j are bigger than big N, then this means that the distance between x, what? I and x j is what? Less than epsilon over 2. Everybody happy with that? So we've just taken care of showing that past some point in the sequence, all the terms are close to each other, right? Okay. What else? What else can we say? X and k converges to x. I agree. Okay, so let's say this converges to x implies. Yeah, let's call this n1, let's call this n2, such that, help. Sorry about that. Just coughed. Okay, so there is big N2 such that anytime you have something bigger than, little n bigger than big N2 implies, okay, we have to be a little careful here, but yeah, I mean, we're just saying past some point in the sequence, the subsequence converges. Now, would you agree I could write this in terms of k, or I could write in terms of n? And just for ease, I'm going to write in terms of n. So such that whenever n sub k is bigger than n2, this implies the distance from x sub nk to x is less than epsilon over 2. Yeah? Okay, help me here a little bit. So what is it I would like to say? We have to be maybe just a little careful here. So I want to eventually show that past some point in the sequence, in the big sequence, I can get within epsilon of x. So what point should that be? Okay, you'd like to take the max of n1 and n2? Is that right? Okay, let's see if that works. If it doesn't, we'll have to modify a few things, but this is certainly the first thing to try. Let's let big N be the max of n1 and n2. Okay. And now the goal is to show, so if n is bigger than big N, then what can we conclude? Well, first we're going to bound the distance from xn to x by the triangle inequality, which would be what? Oh, well, now we have to sort of specify an intermediate point to compare to, right? Maybe that's an issue, something we have to deal with first. Right, so I'm gonna finish writing this out, but this is sort of where we're heading. So I might have to insert something here, but the point is xn, if it's bigger than big N, the claim is that there's some other point x sub what? nk that I want to compare to, and the only problem is, this is a huge problem, is that I actually haven't said what x sub n sub k is, right? So I probably want to insert here before this line a line in between, right? So the line in between should say what? Pick an n sub k bigger than n. And do we know that one exists? Yeah, because it's a sequence, and of course, a subsequence, it has to eventually, there are infinitely many terms and only finitely many things before nk. So in fact, I'm gonna just do that here. This is less than or equal to this plus this in fact, for any n sub k bigger than n, this should be true, right? For any n sub k bigger than n. We should actually fix one so that we can finish this argument here. So I'm just going to fix one. I don't care. And now this is less than what? Epsilon over 2. This is less than what? Epsilon over 2 by construction, which is epsilon. And so what have we shown? We've shown that no matter what epsilon you give me, this distance is less than epsilon as long as, and I found an n for which that works. Okay. So given epsilon greater than 0, we found an n that works. That shows convergence of xn to x. Okay, everybody happy with that? So we've used the Cauchy not the criterion, the Cauchy definition here in a very essential way. So what does this mean? Oh, this means that x is complete, yeah. And this is true for any sequence. So I'll just write a sentence that xn was arbitrary. Big X is complete. That's the end of the proof, actually. Okay, very nice. So this actually now shows that 0, 1 is a complete metric space, right? So corollary, 0, 1 is complete. Oh, not only that, if you want to look at some compact set in a larger space, right? Isn't the the K cell complete? K cells are complete. What K cells? I mean the ones in Rn. Lots of things now we know are complete. Okay. So does this mean that can we show? Do you think that Rn is complete? It's not compact. Do you think Euclidean space is complete? How many people say yes? How many people say no? Objection?
Oh, no,
It's just a guess, and I applaud you for being bold and taking a stand against the opinions of others. Do you think it's good though? It's good, but it's not the right answer. Why is Rn complete? Can you see why? We've just shown that compact spaces are complete. Even though Rn is not compact, can you show that it's complete? Can you show that every Cauchy sequence converges? Jenny?
Well, you could show that every Cauchy sequence is bounded, and then from there you can just look at that portion of Rn and show that then since it's contained within a compact space.
Excellent. Excellent. Good. So that's in fact our strategy. I just noted here in my notes here, I wanted to mention one more thing. Another example of a complete spaces. If you take a closed subset of a compact set, it must be complete, right? Because they're compact. Oh, nice. So in particular, Cantor sets are complete, right? Example, Cantor set. That's closed. The standard middle thirds Cantor set is complete also. And as another corollary, we should mention that Rn is also complete. And it's basically easy to justify because they are in fact Cauchy sequences are bounded, and bounded they'll live in a bounded subset of Rn. So let me just write the proof idea. If Xn is Cauchy, it's bounded. Did we show that last time? I'm trying to remember if we showed that last time. But if not, can you see how to show it? Picture points are getting close to each other. Yes? So you give me an epsilon. Past some point in the sequence, all the terms are within epsilon of each other, right? So maybe past some point in the sequence, all the terms are within epsilon of each other. Therefore, only finally many are not. So then basically take one of these things and look at the distance to all the points outside and take the maximum. And that with epsilon, right? It is bounded. Why? So here, I don't care. Take epsilon, let epsilon be 1. Or just to be interesting, let epsilon be 17. Okay. Then there exists an n such that the distance from xn to xm is less than 17. For all, such that for all n and m bigger than big N, this distance is less than 17. So I don't care which one you pick, just pick one that's beyond xn. So consider, so let R be the maximum of the distance from x sub, let's say, big N to x1 through the distance from x sub big N to x sub n minus 1, add in 17, and this claim everything is within this ball. So the sequence is bounded by a ball of radius r around x sub n. There. Okay. If it's Cauchy, it's bounded. If it's bounded, it's in a ball. If it's in a ball, it's in a, you could just make it, put it in a closed ball or a closed K cell. So it's in, so this ball is in some K cell in Rn. So this ball is complete. So this xn converges because the ball is complete, because the K cell is complete. Nice. So what have we just done? We've shown that if it's Cauchy, it converges. So this shows that, in fact, Rn is complete. Nice. Okay. Any questions? Yes, Drew. Are products of complete spaces complete? If it's a finite product, yeah. If it's an infinite product, we haven't talked about what an infinite product is, but you have to be very careful. Okay. Excellent. So what's this mean? What this means is, in the space we care most about, Rn, to be Cauchy is the same as being convergent, right? So I don't need to know what the limit is to show that a sequence actually has a limit. So let me just give you an example. Suppose I want to look at this sequence. Xn is the sum of the first n reciprocals. Does this converge? Would you agree that this is a sequence? The first term is 1, the second term is 1.5, third term is 1.83333, fourth term, etc., right? Now, if you just write out the first few terms, it's unclear whether it converges or not. I know you know the answer to this, but if you're just looking at on the face of it, I mean, come on, this thing is like growing really, really slowly, right? In fact, you know, you're going to have to go very, very far just for this thing to get bigger than the number 4, right? So it does, you know, it does this. Okay, so and you know, it just takes a long, long time, right? So, you know, you do this at a rate of 1 per second, it'll take, you know, a century for it to actually get past this point on the board. Right? Okay. Does it converge? How could I tell if it converges or not? Well, I could ask, is it Cauchy? Right? If I could show that it is Cauchy, then it converges. If I could show that it's not Cauchy, then it doesn't converge, and we say diverge, right? It diverges. Okay, so here, this is what's cool. Check this out. Let's look at this difference. This is, in fact, what I'm interested in looking at, the distance from xn to xm. This is brilliant idea. Look at the difference. What is the difference between the sum of the first n reciprocals and the sum of the first m reciprocals? If, let's just say n is bigger than m. What would you say that difference is? It's just the sum of the reciprocals from n to m, right? From the n plus 1 thing, perhaps. So maybe go m plus 1 plus 1 over m plus 2 plus ... through 1 over n. Would you agree that that's what that difference is? Oh, but wait, what's that? Would you agree that this is, in fact, I can take off the absolute value if I assume one is bigger than the other, right? Would you agree that this is at least as large as n minus m over m? Let's see, do I have that right? How many terms are there? There are n minus m terms, yes? And would you agree that each such term is bigger than 1 over, should this be an n here? 1 over n. Would you agree with that? Yeah? Okay, that is cool. Well, what's this? This is 1 minus n over m. Oops, m over n. Right? Okay, so check this out then. Look, if I let m be 2m, you can't stop me from doing that. If I go twice as far out, then what this is saying is x sub, sorry, m is bigger than n. Let n be 2m, excuse me. If I go twice as far out, then what do I see? I see x sub 2n minus xn is bigger than what? 1/2. And that's true for every n. Does this sequence have any hope of being Cauchy? No, it can't be Cauchy, because as soon as you let epsilon be less than 1/2, you will never find a point in the sequence beyond which all the terms are closer than 1/2. Because I've just shown you pairs of terms infinitely far out as you'd like to go, where they're bigger than 1/2. Sequence is not Cauchy. So, it doesn't converge. Brilliant, right? I don't need to know what the limit is or what the proposed limit is to show that it converges or doesn't converge. Okay. Nice. Okay. Let me do another example, and I'll let you complete this example, but I'll just show you an example where you have no idea what the limit is, but you could show it converges. Example, suppose x1 is 1, x2 is 2, and you now define recursively xn to be the average of the previous two terms. That's an interesting process. Does this converge? Well, I have no idea what its limit is, but it's very easy to show that it's Cauchy. I'm not going to do it, but the point is, you see, when you have a limit defined like this, or a sequence defined like this, you may not have any idea what the limit is, right? But Richard can say authoritatively it converges because it's Cauchy. And because this is a sequence of what kind of numbers? Real numbers, right? Not true if this were the rationals, right? Because we wouldn't know that the limit were rational. Okay. In fact, it might not be. But a very, very nice example. What kind of where do such sequences arise? Lots of places. Recursive methods for finding roots, right? This is Newton's method, right? You use sequences like this all the time. You can show it converges theoretically without knowing its limit. Beautiful idea. Okay, excellent. So now let me really blow your mind. What if a space is not? What if a space is not complete? So here's a question you might ask. If X is not complete, like the rationals, is not complete. Well, that's not a good thing, right? But what might you hope to be true? Maybe some Cauchy sequences converge, but what's a bigger thing you might hope to be true about a space that's not complete, like the rationals? Maybe it has gaps, but Lindsay? Okay, so what you're saying is if I have a universe that consists of only Q, maybe I could say it converges, not in Q, but to some bigger space, right? Which I haven't yet defined, right? Because it happens that Q can be embedded in R, which is complete, right? And so here's a natural question to ask yourself. If I have an arbitrary metric space that isn't complete, can it always be embedded in a space that is? Oh, interesting. If X is not complete, can it be embedded in one that is? And the answer is, well, so here's an example, of course, Q. So an example here is Q, and it can be embedded in R. What do you think the answer is? Yes, that's a very, very beautiful theorem, and you're going to prove part of this theorem in your homework, next homework. So here's a theorem. Every metric space, this is an amazing theorem, actually. I've assigned half of the theorem to prove and the other half for you to read. Every metric space XD, I'm just telling you what the metric is, it's the distance metric on X, has a completion which I will call x star d. And what do I mean by the completion? What I mean is there's a way to define a big space that has, as a subset, this smaller space, such that the metric on the big space, when restricted to this smaller space, gives the same metric as the small space. Amazing. Amazing idea. So let me sort of sketch the idea for you, because you'll encounter it on your homework. But yeah, in fact, I know. So the question you're asking is, in what sense is this completion? There could be lots of completions. In what sense is this completion unique as it's defined? And I'm about to answer that question. Right, because Q can be better than R squared, right, if you want. That's sort of what you're saying. So this theorem says that there is a completion, but the proof actually shows you exactly what completion it is. And it's the construction is actually unique as it's defined. But there could be lots of completions that aren't unique. I mean, that aren't isomorphic. But the one that the proof suggests is unique. So here's the idea. Given x, whatever the space is, whenever I say x here, think Q. Okay, that's maybe the best way to grasp what's happening here. You think rational numbers whenever I say x, but x could be any metric space. What I'm going to do is, let's see, take a wild guess. How am I going to get at those things that aren't already in the space? We've done something like this before. Yeah, if my space has some gaps in it, well, I can't talk about the gaps because I don't have anything don't have a way of defining them. Maybe I can get at those gaps using the things that are already in the space. Namely what? The Cauchy sequences that are in the space. So in fact, what we're going to do is, this is the beautiful idea, let's let x star be the set of all Cauchy sequences So this is the set of all Cauchy sequence in X. Now, of course, there's a problem with this. If I just stopped my definition here, which I'm not going to do, but well, temporarily. If I stop my definition here, there are way too many things in this space. It's huge, right? So imagine the rationals. There are lots of Cauchy sequences that converge to 0, right? So I don't want to say they're all different. So I'm going to actually look at the set of all Cauchy sequences under a equivalence relation. Good. Under an equivalence relation. And the equivalence relation I'll call tilde. And we have to say what that is. Where two sequences, this is a sequence, is equivalent, Pn and Qn are equivalent. That's what I'm saying. They're equivalent if what? Yeah, so you want to say this in a way that doesn't refer to the limit, right? The natural thing you want to say is you want to say they're equivalent if they have the same limit. But not all these Cauchy sequences have a limit, right? So instead you say they're equivalent if their difference gets small. Very good. Excellent. If, this is such a beautiful idea. If I let the limit as n go to infinity of the distance from Pn to what? Qn, if that limit goes to 0. So that's one big idea. Period. So now these are the things that we'll call equivalent. And now what's beautiful about this is you can define a metric on this. So if you don't mind, I'm going to call, let me call this sequence, there's big P for the whole sequence. That's the whole sequence Pn. And this one I'm going to call the sequence Q. Yeah? So now P and Q, big P and big Q, they are points in this metric space. And each one is a sequence in the other metric space. Yes? So now let's define a distance between them. What's the distance, which I'll call delta for distance? Yes?
P and Q into being different. Oh, are you defining them to be in different equivalence classes and PQ be the different equivalence classes?
Oh, sorry. I don't mean this particular Pn and Qn. Sorry. Let me. Thank you. This was a definition, and I just committed a very serious error, which is to try to do too many things in one line. So let's say for P and Q in X star, let's let D, big P, big Q be. And I will write out later P is like little pn and Q is little qn. Okay. Yes. They're entire equivalence classes, but you can always pick a representative. Yes, thank you. Much better. It's actually what I had in my notes, but I tried to. Anyways, I should not depart from my notes. Okay, here we go. Delta PQ. What do you think the distance between, how do you measure distance between two sequences or equivalence classes of sequences? Here's big P. Here's big Q, which has as a representatives Pn and Qn. Sorry, who's saying that? Oh, Katie.
Yeah, so similar to when you said the limit goes to 0, if we define a sequence by the difference between Pn and Qn,
Good.
then there's
Nice. So this is a limiting distance. And here, here you let Pn and Qn be representatives of P and Q. Because these are equivalence classes, aren't they? So now what's a question you have to ask yourself? I've just defined this in terms of representative. Yes?
Well, I think you're getting at, is it well defined, but I was going to ask a different question.
Okay, you can ask your question in a minute, but yes, one of the things you have to show is that this definition is well defined, and that's part of your homework. Is it well defined? Of course, the answer is yes, it is well defined, but you have to show that. Okay? If you pick two different representatives, will you get the same distance? And of course, the answer is yes, because all these things are Cauchy, and so do a little work there. Yes. Okay. Question?
So I'm wondering, the definition seems to imply that this distance is some point that exists within the metric space that we're talking about, or within X star. And I'm wondering, how do we guarantee that it's not another point that's in the completion as opposed to just the metric space itself? So we've taken the limit of two
Yeah.
sequences.
Yep. So sorry, here we've taken the limit of the distances, and you get a number. That number is defined to be the distance between the sequences P and Q.
How do we know that that number is a number in X?
It's not in X, it's in R, because a metric always spits out a real number. Yeah, so we can talk about limits in R. Okay, good question. Yes, Emil.
How do we know that limit converges or that limit exists?
Ooh, excellent question. Excellent question. So that's, again, something you have to show. Why does this limit exist at all for any two sequences P and Q? And it boils down to the fact that these sequences actually are Cauchy. Right? So, I mean, you have to do some work here, and that's part of your homework here. Okay? Interesting. So then once you have this, the part that I just asked you to read, you can see a sketch of this. The way X star is defined, it's actually unique up to isomorphism. So then the claim is, first of all, it's complete. Oh, if you want a challenge, prove this. There's actually a a very, very good challenge here. X star is complete with X. What is X? Somehow it's isometrically embedded in X star. Now I have to say what this means. Isometrically embedded means there is a bijection with a subset of X star that preserves distances. Okay? Can you see what that bijection should be? Which sequence in X star should I correspond with a point P in X? What sequence should correspond to it? Yeah, P, 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 right? That's exactly what it is, right? Okay. And this is a what's called the completion of X. And if you do the completion to Q, you get R, not R squared. Okay, so it's actually a unique construction that we have here for the completion. And in fact, this is the other way to construct the real numbers. Okay, we've just done it in a slightly different way. So we saw Dedekin's cuts as a way of constructing Q from R, R from Q. But this is another way to construct R from Q. The reason that that we didn't do it earlier is we needed some machinery. We had to develop the notion of metric spaces and convergence and things like that in order to talk about this. Whereas Dedekind cuts, you don't need any of that. But both of these constructions happened historically about the same time, 1872 or so. Okay. Question?
Would you have problems if the distances under the metric are defined in R, and if you're trying to construct R from Q?
Oh, I see. Yes, I see what you're saying.
Though I guess we have a different...
Yeah, well, so in that case, you're not so worried about the metric, right? You can't stop me from making this construction. Yeah, you can't stop me from making this construction, but it would not make sense until I've defined, the metric, I guess, and to talk about what it means to be isometrically embedded. But you could talk about sequences where terms eventually get close to each other. Yeah. 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 Let me think about it, see if I have a better response to that question. But I don't think you need to worry too much about it if you haven't talked about what the isometric embedding is. Let's take a couple-minute break, and after the break, we want to do a few other things as well. Okay. Okay. Excuse me. Let's resume. So there are a few other, other concepts which are associated to sequences and subsequences, and that's the notion of monotonic sequences and lim sups and lim inf. So we should say a little bit about bounded sequences. Now, we've already said something about bounded sequences, but I should define what it means to be monotonic. So monotonically, that's a long word, increasing sequences are what you think they should mean. Namely, successive terms are bigger than the previous terms, or at least equal to. Okay? We call this monotonically increasing, just means it's monotone. It's in one direction. Okay? We have the same notation, same adjective monotonically for decreasing sequences as well, which is just sort of what you expect. Successive terms are no larger than the previous terms. Okay? Okay. So here's a theorem which many of you learned in calculus. Should be very easy for you to prove now. And that is, if you have bounded monotone sequences, and it doesn't matter whether it's increasing or decreasing, but pick one, bounded monotonic sequences converge. I think in the calculus courses here, you look at increasing sequences, the bingo theorem, bounded increasing sequences go to a limit. I think that's the way to put it, right? Okay. Bounded monotonic sequences converge. Can you prove this? What do they converge to if they converge? So here we go. If you're in the real numbers, this is all talking about real numbers. They're increasing, and they're bounded by some bound b. Why do they converge? What do they converge to if they converge to anything? Their supremum. Very good. So tell me why they converge to their supremum. Proof. So in fact, you just stated something we could put in the theorem here, right? To their what? If it's sup, if it's increasing, or infimum if it's decreasing. Okay. We'll just do one direction. Proof. So suppose you're given Sn. Let's let S be their sup. We feel like we've done this before. The sup of the range of Sn. That's really what we're doing, right? Take the set of all things that values it could achieve. Okay? Okay. So that is sitting in this picture, like right here. Help. Why does it converge to S as a sequence? Sure, S is a limit point of these points, but why does this converge as a sequence? And to keep this in perspective, imagine this could be x1, but x2 could be over here. x3 might be behind. Oops, no, it can't be, because it's monotonic increasing. Yes, so you see, we have to use this fact somehow, because otherwise you could have points that do this, right? Good. Help. To show convergence, for every epsilon you have to find a n, beyond which everything is within epsilon. So let's take this to be epsilon. Can you find a point beyond which everything is within this ball of S? Yes, because S is a supremum. We know that there is a point that is in here. Now, why are all points past some index in here? Because they'll have to be bigger. That's it. That's basically it. And you could make me write it down, but I guess I will just sketch. Let me just sketch, because I feel compelled to say something. Then for all epsilon, so for all epsilon bigger than 0, there exists a big N such that S sub big N is in between, is bigger than S minus epsilon, and of course less than S. Less than, or I guess equal to S perhaps. Oh, but then what? But then for all little n bigger than big N, S sub little n is bigger than S sub n, big N, less than or bigger than or equal to, and this is bigger than S minus epsilon. So S, and this is less than or equal to S. So this n works for epsilon. I'll just finish there. That's the idea. Okay? Yes, Jenny?
What other metric spaces could we possibly do this for besides the reals? Obviously, it has to have something which has an order on it. But, what other sort of metric spaces would we
Yeah, I don't know that. I don't know that there are any popular theorems, anyways, extensions of this, but you could certainly, I guess, create some weird metric spaces that would have analogous theorem. Yeah.
Anything with the bijection.
So certainly, an isometric bijection to R would be R. It'd be isomorphic to R in some sense. Isometric to R. Yeah, okay, good. So there's a theorem we can just polish away. Now, it may be the case that that you have sequences that don't converge to anything, but they do have subsequential limits, so we should say something about that. Oh, maybe I should also say this. So we should say something just about regular boundedness. So some sequences actually diverge, not because they bounce around, but because they keep going in one direction, right? So we'll write Sn goes to positive infinity. It's really just a symbol. It doesn't really mean anything except that it means that, so if, what's true? Well, if for any big M in R, any number you name, there exists an n, a big N, such that little n bigger than big N implies S sub n is bigger than M. So what you'll notice here is that this looks a lot like the definition of convergence, except you're at the very end, instead of saying you're within epsilon of a limit, you're saying you're bigger than M. Right? And so that's the sense in which you want to say Sn converges to big infinity. It's kind of like you imagine the number line here, and you have something at the very end. And you're asking to be within something of the very end. That's really what you're asking. Okay? So that's why we have this kind of notation. And similarly, you can write Sn goes to minus infinity, and it's the same kind of definition except what? With, at the very end, you have Sn less than M. Dot, dot, dot. Fill in the blanks. Okay. Okay. Here's another important idea. Let's let, given a sequence, let's let, I'll just let E be the set of all possible subsequential limits. Look at all the subsequential limits that the sequence could have. Okay. Now, of course, if the sequence just keeps going off to infinity, then of course we may allow this to have plus or minus infinity as a subsequential limit. There's no harm in doing that. Okay. And so now you could ask something about this set. Your book shows, in fact, this set is always closed. Okay, I won't do that proof here, but you can read about it. But this set, as a set, actually might have a supremum and an infimum. So, in fact, let's just go ahead and give those names. So I'll let S superstar, get it? Superstar, be the supremum of V. And I'll let S substar be the infimum of E. Now notice, these always exist, because this is extended reals we're considering. It might be plus infinity or minus infinity, yes? Okay. Now, these actually have alternate names. So this is sometimes called the lim sup. Okay. And this is sometimes called the lim imp of the set E. Okay? Or sometimes you hear this term, upper limit. I think this is the term the book uses. Lower limit of E. Okay, these are all alternate names for these things. In modern parlance, this is often lim sup or lim imp are the terms we use. Okay? Sometimes you'll see lim sup and lim imp with symbols under them, although you don't need to put them here because we know what it means. But you might say Sorry, I shouldn't say Sn. This is lim sup of Sn and lim inf of Sn, not E. E is just what's defined in terms of Sn. Sometimes you'll see the n goes to infinity symbol there. You don't have to have that there because we have some sense of what this means already, but it just indicates the index that we're using. Okay. Here's an alternate way to think of lim sup and lim inf, and this is the one that I find most useful. I don't know that it's mentioned in your book, but it's certainly one that helps explain the notation. Why do you think it's called lim sup? And it's not because we're chopping off things and putting them in broth. Good. Oh, well, something like that. It's the limit of a certain set of suprema. And really what you're doing is you're looking at all the terms past a point. So look at all the k bigger than n, take their supremum, and then take the limit as n goes to infinity. So the net effect of this is it chops off all the initial behavior of the sequence. Okay? And you're only looking at sort of the long-term behavior. And that's why this concept actually arises, believe it or not. We'll see that when we talk about ratio tests. But here we go. This is similarly lim of an infimum of k bigger than n of S sub k. Now, I'm not going to prove this, but you can show that this actually is equivalent to the largest sequential limit and small subsequential limit definitions. Let me do some examples, and then we'll call it a day. So here's an example. Tell me what's got to be true about the lim sup and lim inf if the whole sequence converges. Yeah, if this whole sequence converges, guess what? The lim inf has to equal the lim sup. And they both have to be what? S. There's no other thing it could be. You're just chopping off the initial behavior. You're looking for the lowest subsequential limit and the upper subsequential limit. All subsequential limits have to be S if it converges. All right. Good. Let's look at a sequence where you don't have that happening. How about this one? How about 0.1, 3/2, 0.11, 4/3, 0.111, 5/4, 0.1111, 6/5, ... There's a sequence. Maybe I should put braces here to indicate it's a sequence. Can you see what its lim inf and lim sup are? On one hand, some of those 0.1s, these things are going up. And then there's the 3/2 and 4/3, which are going this way in some sense, like this, right? Can you see what the lim inf and lim sup are? I think the lim sup is 1, and the lim inf is 1/9. I have the wrong thing in my notes here, actually. Okay. Lim inf and lim sup. Okay. If I were to say that something was bigger than the lim sup, what would that really mean? So here's the lim sup. If I were to say that a number is bigger than the lim sup, what is that? What's another way of saying that? It means that, does it mean that all the terms are necessarily bigger than x if x is bigger than the lim sup? No. But it must mean what? Must mean what? Not all the terms are necessarily bigger than x, but can you say eventually all the terms are less than x? Yeah, eventually that has to be true if x is bigger than the lim sup. There's a theorem in your book that makes that precise. But really, you can make similar kinds of arguments that we made before with limits, with lim sups and lim inf if you're just careful. Okay? Okay, that's good. Next time, we're going to start talking about series, which are special kinds of sequences.